computer audio. Okay, so we're off and running. This is chapter 9, gas turbine systems. We'll just cover the portion of it which I think it would be interested and important to you. And I have some good news. First, I'll drink a cup of coffee, so maybe I can talk faster and get through this thing faster without dulling you to death. The other thing is, I think I've learned how to handle my screens better, how to pull them up and manipulate them and so forth, where what we see or what you see on the screen is what I need you to see. I find this gas turbine systems very interesting, and they're especially interesting now because they're so popular. And I'll explain that as we go. So let's get started. All right, I'm share my screen. Let's see, let's start with this one. Share. And I've learned how, let's put me down at the bottom. All right, I've learned how, like if I want to bring up another screen, all I got to do is this. And well, we don't need that now, but we will. All right. Gas power systems. I call them gas turbine systems, gas powered systems. All right, learn it. And there's not as many slides here. There's 23. I've pared them down pretty well. So what are our learning outcomes, our objectives? We're going to conduct an air standard analysis of gas turbine power systems based on the Brayton cycle and its modifications, some modifications, not many, including we're going to learn to sketch the TS diagram and evaluate property data at principal states, apply the mass, energy, and entropy equations. Not too much entropy now. I'm going to slack off on that a little bit. Determine the net power output, the thermal efficiency, and the back-work ratio. So we're going to learn how to do all those things. All right, let's talk a little bit of general about gas turbine power plants. Gas turbine power plants are more quickly constructed, less costly, and more compact than vapor power plants we discussed in Chapter 8. Sure. Gas turbines are suited for stationary power generation, as well as for powering vehicles, including aircraft propulsion and marine power. We use gas turbines. Of course, turbines are used in almost all jet engine. We're not going to get into those. Our boats. We're going to strictly limit our discussion to power generation. Gas turbines are increasingly used for large-scale power generation. Now, there's something in my eye. There's a relatively new, I say last 10 years old, gas turbine station, power station in Entergy's portfolio out on Beasley Road toward Jackson. We'll talk about it later. Being gas turbines, what do they fuel with? They fuel with natural gas, which due to fracking is not relatively abundant, it's actually very abundant. So we've got sort of two basic types of gas turbine systems. They all are configured with a turbine, a compressor, and a combustor. And the way these work, the compressor takes atmospheric air, compresses it up to about a factor of 10 to 15. So if 1 bar enters here and you're using a pressure ratio of 15, it'll compress it up to 15 bar. Then it goes through the combustion chamber where fuel is added, and of course it combusts and burns. But it's not like an internal combustion engine where the combustion actually moves the piston and drives and ends up turning a drive shaft. What this combustion is all about is adding heat. That's what it does. It adds heat. And the amount of fuel compared with the air in the fuel-air ratio is so low that we can still consider it an ideal gas, air, the ideal gas air, even after it enters the turbine with the fuel exhaust mixed in with it. because there's so little that there's still the ideal gas equations are fine. Now, in an open system, it takes atmospheric air in here, compresses it, goes through the combustion cycle, comes out of the turbine, it creates work, and then is discharged to the atmosphere because it's relatively clean burning fuel. Of course, the work of the turbine has to go two places. About half of its work goes just to run the compressor, and that leaves about half of the total work available to go and drive the generator, your electric generator. But even though it takes half of its turbine's power to drive its own compressor or the compressor on its shaft, it's still a fairly efficient way to produce electricity as far as cost-wise. Now here's a closed system. We'll use those mostly when we get into the combined system at the end of this discussion. But in a closed system, the output of the turbine, which is it's low pressure now, but it's still pretty hot air, can go through a heat exchanger, and you can extract some nice heat out here to use to do some other things, mainly to act as the heat input to a separate but connected through the heat exchanger Rankine cycle. And then that air goes back into the compressor, or it can be discharged to the atmosphere. It really doesn't matter because as far as the cycle goes, if this air is coming out hot here and it's discharged to the atmosphere, then somewhere in the atmosphere, it eventually cools back down, and you can imagine it's cooled down and then pulled back in here. Of course, this is different air sucked in and comes out. But whether this is a closed system here or open, the analysis is pretty much the same. All right, considering the open system, air is continuously drawn in the compressor where it is compressed to a high pressure. All right, we said that. Air then enters the combustion chamber or combustor where it mixes with fuel and combustion process occurs. Combustion products exit at elevated temperature and pressure right here. Combustion products expand through the turbine and then are discharged to the surroundings. Like I said, part of the turbine's work, about half of it goes to drive the generator, and about half of it is on the same shaft to drive the compressor. The compressor puts pressure energy in, then the combustor puts heat energy. So you end with high pressure, high heat coming in the turbine. You get a lot of nice work out of it. So here comes the fuel, and of course the fuel is natural gas. And the fuel, the combustion products, hot combustion products and the air enters the turbine. Like I said, the fuel products, the fuel mixed in with the air has very limited, well, let's put it this way. You can still treat the thermodynamic fluid coming through the turbine as an ideal gas with almost no loss of accuracy. Now we look at the closed system. Operates as follows. Gas circulates through the four components: compressor, heat exchanger, turbine, heat exchanger. This heat exchanger takes Q in. This heat exchanger rejects Q out. As gas circulates through the four components, turbine, compressor, two heat exchangers at higher and lower operating temperatures respectively. Let me read that again. As gas circulates through four components, turbine, compressor, and two heat exchangers at higher and lower operating temperatures respectively. The turbine and compressor play the same role as the open gas turbine. As the gas passes through the higher temperature heat exchanger, it receives energy from heat transfer from an external source. That is combustion. That's the way they're talking about. The thermodynamic cycle is completed by heat transfer to the surroundings as the gas passes through a low temperature heat exchanger. Now this is the gas turbine power plants, sheet 5 of 5. the heat transfer associated with the higher temperature heat exchanger of the closed turbine originates from an external source, which may include external combustion of biomass, almost any kind of gas, because you just get using the gas to generate heat. It's not like an internal combustion engine. And you can use the biomass, solid waste, municipal solid waste, not sure about that. You got to get a gaseous. Fossil fuels, natural gas, and other combustibles. Waste heat, you can use waste heat from industrial processes to generate the heat in. Solar, a thermal energy, or a gas-cooled nuclear reactor. But generally, I'd say 95% of the gas turbine systems use natural gas as the fuel. Okay, we can conduct an elementary analysis of open gas turbine. To do an elementary analysis, we have to make some assumptions. They're pretty valid assumptions. The first is the working fluid behaves as an ideal gas. The temperature rise that would be brought about by combustion is complicated. It's accomplished by heat transfer from an external source. So here's what that means. All right, we have combustion going on right here. We model that as a sudden influx of heat in BTU per hour or kilojoule or kilowatts of or whatever. We don't describe the combustion process from a chemical standpoint. We describe it as a sudden infusion of heat. So we avoid complexities. Like I said, we avoid the complexity of the combustion process and the change in composition during the combustion process, which simplifies the analysis. If you want to look at the combustion process in detail, you go to chapter 13. So I don't expect any of you would. I wouldn't be. In a cold air standard analysis, the specific heats are assumed constant. We will not use the cold air standard and constant specific heats. We will use the tables. So this is sort of redundant here, but let's go through it again. All right, this is an open air standard turbine power plant. Energy transfers by heat and work are in the direction of the arrows. So I think we've pretty much gone through that. State 1, air is drawn in from the compressor to the surroundings. State 1 to 2, the air is compressed to a ratio of 10 to 15, maybe even 20. 2 to 3, we add heat, and then from 3 to 4 is the turbine work process to drive the shaft. Right here. Air returns to its surroundings here, and then we bring in some new air. Again, this air discharged meets the EPA requirements. This is sort of like a exhaust from your engine, gasoline internal combustion engine, although it's a lot cleaner. And this completes the thermodynamic cycle. Like I said, you're blowing out hot air here from the turbine, and you're pulling back in cool environment, air from the environment back into the compressor. I don't know if, let's see. Yeah, I think that's pretty much redundant what we did. All right, so let's look at this slide. Let me do a share and make sure you're seeing what I'm seeing. Yep, you are. So this is the Brayton cycle right here. And 1, 2, 3, 4, 1. And this cycle from 4 to 1 can go through a heat exchanger, or 4 can be discharged into the atmosphere, and then 1 is pulled back out of the atmosphere. Cool ambient air here, hot air goes here and mixes with the ambient. Probably goes up a stack, I would think. I'm not sure about that. One of the key operating parameters of a Brayton cycle is the pressure ratio. That's the ratio of P2 over P1. And like I said, that can run from 10 to maybe up 16 or so. So if you had air coming in at normal atmospheric pressure, which is about 1 bar, it's actually 1.01 bar. We'll call it 1 bar. If the pressure ratio is 12, it would exit at stage 2 at 12 bar. It would be constant at 12 bar through the heat exchanger, but it'd pick up a lot of temperature, then go through the turbine and create a lot of work, turning those turbine blades and turning the turbine shaft with some torque on it. About half the work goes to the compressor, half the work goes to the generator. Then you've got, coming out of here, the temperature is still quite hot in this air. That's why there's an opportunity here to use a heat exchanger to grab some of that heat for another process. We'll talk about that later. So here are the ideal equations. And again, he structures his equations where he always gets a positive number, even for the compressor work. I don't like to do that, but you can if you want to. I like to get a positive work for the turbine and negative work for the compressor, then algebraically add them together instead of making sure I've manipulated the actual equation to get a positive number for the compressor and then subtract the compressor work for the turbine. Either way. But the turbine, absolutely, the work of the turbine, and this is isentropic. Well, no, this is not isentropic. These are actual H3 and H4s. So this is the actual work of the turbine per pound on a rate basis is H3 minus H4. Remember, our equation, basic equation, said the sum of the energy streams coming out minus the sum of the energy streams coming in is equal to plus Q minus W. So H4 minus H3 equal minus W if Q is 0. So that means that W is equal to H3 minus H4. That's what he has. That's fine. This heat addition here in the combustor, they call it a heat exchanger now, but that's the combustor. It'll come out, it'll come out H3 minus H2. But the compressor, let's look at it, all right? The sum of the streams coming out, which is, that would be H2 minus H1, or M dot H2 minus H1 equals minus W. So when you go to solve for W, W is going to equal to H2 minus H1. Well, they have it. No, I'm sorry, it's H1 minus H2. They have H2 minus H1. As long as you think about it, you're going to be fine. It's not going to trip you up. But you see, one thing to point out, how simple these equations boil down to at each of these control values. Just a very simple mathematical operation. And if you wanted the total Q in, you would multiply by the mass flow rate. Same if you wanted the total work out of the turbine, you'd multiply by the mass flow rate. So it's very simple equations that it all boils down to. So if we look at the thermal efficiency, that's the net work, divide the net, NET, WORK. 2 words, not network like you know what I mean. The net work over the energy in. And you can write M dot, you can get these works, you can have the M dot times the H's, M dots times the H's here, but regardless how you write it, the M dots will cancel out and you're left with these 2 enthalpies. Now again, when I write my compressor work, I'll have H1 minus H2. I'll have plus H1 minus H2, and that's going to be a negative number, so you'll have this positive number algebraically combine with this negative number, and it'll be a subtraction. You're going to get the same answer if you're just careful. Then H3 minus H2 is the amount of heat goes in the combustor per pound. And like I say, for this system, which has steady flow, same mass going in equals same mass going out, so the mass cancels out and you're left with that formula. The back work ratio is simply the turbine output. No. It's the compressor work, which is H2 minus H1, or I like to do H1 minus, let's see, H1 minus H2, I do. I get a negative number here. That's okay, because you're looking for ratio. This is the turbine, total turbine work. This is the compressor work. So as I've told you, that runs about 0.5 or 50%. So if this is 100, say horsepower, that's how much the turbine is putting out, but the compressor is chomping up about 50 horsepower, or half of that. But still, even though a lot of the energy goes to drive the compressor, it's still a good economical process. Let's see, what does he say here? A relatively large portion of the work developed by the turbine is required to drive the compressor. For gas turbines, this back work ratio ranges from 20 to 80%, compared to only 1 per 2% with power plant. As you remember, with the Rankines or the vapor power plant, we have to drive a pump, and it only takes 1 or 2%. Here we have to drive a turbine, it takes from 20 to 80%. But still, this is efficient because, or economical, because the price of natural gas is relatively low. Now, these are the actual performances. These equations above had been developed for mass and energy balances. They apply equally when irreversibles are present and then the absence of irreversibilities. What that means, if I give you a Brayton cycle and I specify the endpoints, enough for you to get the properties at all the values, then you can count what if these are the actual properties, and you have enough that you can look up the enthalpies in the tables, then you get the actual work. We usually don't do it. We don't have it that way. We want to define how well our turbine is performing relative to the best possible performance. The best possible performance, as you probably know, is the isentropic reversible adiabatic work process. So we put that process in place and calculate it, and then compare that to our actual process, and we get a real good idea of how we're doing efficiency-wise. So let's look at the, talks about irreversibilities. Let's get down to, well, he talks about all the irreversibilities in the turbine. You're welcome to read over there, just a few slides. It wouldn't take you for 3 or 4 minutes. Then it talks about, now we look, as you know, we generally use a TS diagram, but it's interesting if we look at a PV diagram, the compressor work ends up being 1, 2, A, B, 1. The turbine work is 3, is actually this whole, that's area. So this is the turbine work. This is the compressor work. And then the difference between is the network we have to go out to our generator. Then we can look on a TS diagram and we can see our heat transfers. For 2, 3, AB2, let's see, 2, 3, VAV2. This is how much transfer comes in from the combustor, the hot heat exchanger where the heat comes in. And then the heat rejected is going to be 4, 1, VA4. So the area that's left here is QH minus QL, and that's equal to the work output of the turbine. Because in a thermodynamic cycle, the sum of the heats throughout the cycle, the algebraic sum of the heats throughout the cycle has to equal the sum of the algebraic works, which means there's a lot of energy transferred going in and involved in a thermodynamic cycle. But as the saying goes, at the end of the day, that energy is neither created or destroyed. Some of the heat that you put in, a lot of it is turned into work. A lot of the second law tells you can't convert all of that work into heat. All of that heat into work. Some of it is going to have to be discharged. So here's a graph that I've been wanting to get to. All right. This is what I'd expect you to draw if I ask you for the TS diagram of a Brayton cycle. 1 to 2 is the actual compression process. Again, this is the lower pressure. This is the higher pressure. We're dealing with a single phase ideal gas, so the constant pressure lines are like parallel arcs with a very mild bend to them, almost straight lines. This would be if we had a 12-to-1 ratio, and this was atmospheric air at 1 bar. This would be constant pressure at 12 bar. So here's the actual process. The entropy always increases on work processes because of irreversibilities. Friction, pressure drop through all the blades in the compressor, bearing loss, bearing friction. Friction is generally the biggest loss. There's some flow losses too, like if you were compressing to a higher pressure and you had some leakage from your high pressure region in your compressor back to the low pressure, that would be some power loss. That's an irreversibility also. Now we compare that with the straight line up and down the isentropic process. Why do we do that? We want to see how efficient our turbine is, or our compressor and our turbine. So with the problems you work in, you'll be given well, let's talk about this, the efficiency. Now he's talking about the turbine here. And I like to use that eta TS, sub TS, for turbine isentropic. N, I call it N, it's eta, it looks like an N, then it's script N, TS. It's equal to the work of the turbine actual, and they have it per pound mass. You don't have to, you could have WT over WTS, and WT has got an M dot times the H's, and the M's going to cancel out, but this is a good way to show it. Work of the turbine actually per pound of fluid passing through it, the work of the turbine isentropic. And the isentropic is going to be on the numerator and the denominator, on the bottom, the biggest ratio. You can never have more than one, so you want to make sure you've got a number that's less than 1. In a turbine, this is the ideal work, and you won't work out. You never get as much work out as you want, as ideal. So the actual work is H3 over H4. The ideal work, reversible adiabatic isentropic work is H3 over H4x. And that is the ratio. We sometimes express it, but normally express it as a percentage, 80%, but in your calculations, you'd use 0.80, 0.80. Okay. So that is the turbine. I don't think you have any, I know some of you had a problem with the way I did my signs and ratios on the compressor we're going to talk about in a minute. On a turbine, my formula agrees with the book. Now let's look at the compressor. This is where he switches things around, and there's really no need to do that, but he does. Look, the work of the compressor is going to end up being like that formula, the energy out minus the energy in equals minus the work, or the work is equal to the energy out minus the energy in, and it's going to be a negative value. Let's see. No, I said that wrong. The work, if we apply the first law equation, we'll have m dot H2, which is coming out, minus H1, which is going in, equal to minus W. If we solve for plus W, we end up with m dot H1 minus H2, not H2 minus H1 as he's got. And the value is a negative value indicating negative work, which is a compressor requires negative work. He switches these around to make them positive. I wouldn't do that. But now this guy's a lot smarter than I am. So you have to accept what he's done. But even though my equation I gave you had H1 minus H2S giving you a negative value on the numerator, it also had H1 minus H2 gives you a negative value on the denominator. So the negative over negative is a plus. You end up with the exact same number as if you used his notation of H2S minus H1, H2 minus H1. And if you use this equation to solve for another, generally the way you know it, you know H1, you know T1 and P1, you know T1, so you can look up H1. As you remember, enthalpy of an ideal gas just a function of temperature. At state 2, all you know is the pressure. So, but you do know state 2S has the same entropy as state 1. You can use that information, and I'll show you how later, to calculate H2S. So now you know H1, you know H2S, and you're given the efficiency of your compressor. So the only unknown in this little problem here is H2. So you can solve this equation for H2, and now you're cooking with gas, you got everything you need. And I'll show you how to find that 0.2S later. Okay, these are the last two slides, but they're the most important slides of the whole thing. This is the combined cycle. So here's what we have. Let me get myself out of the way. All right. Here's our Brayton cycle, air turbine cycle. Air coming in, compressed to high pressure, high temperature. Remember, when you compress air, you want a high pressure generally, and most of the time you don't want a high temperature, but in a gas turbine, you like that high temperature. All of that compression work is sort of usable energy. Goes through the combustor where we get a lot of heat added in. Now it's continuously added in. I said something about all of a sudden added in. Really and truly, it's continuously added in. Then we go through the turbine. About half of the work of the turbine goes in to drive its own compressor on the same shaft, leaving about half or so to drive a generator. But now you're coming out here with this low pressure, but it's hot. It's got a lot of heat energy. Why not design you a heat recovery steam generator to let this hot air pass through here and give its heat off to act as heat input into a Rankine cycle? Why not do that? Absolutely. And that's done. That is most any time you see a gas turbine power plant, it's operating on this combined cycle. You've got the gas turbine sort of on the top, and you got the Rankine cycle on the bottom. You got the best of both worlds. It's really a really nice, makes a really nice little system. And the only heat input, external heat in, is the natural gas in the combustor. That's it. And you get all this work out. So what's some typical values if, you know, a Rankine cycle is doing pretty good to get about 35%. And a gas turbine cycle on its own, I'm not sure it gets that. Maybe 30. Let's say this one gets 30 and this one gets 30 on their own, 30%. When you put them together in this combined cycle like this, that 30 goes up to about 55. And the highest you can get, according to the Carnot, is like in the 70s. So you really, really got an efficient process here. And this is what the power plant that Energy has down here on Beasley Road, and they may have more, but it's, if you head toward Jackson, it's on Beasley Road, almost when you get into Jackson on the right-hand side going toward Jackson. It was built about 10 or 15 years ago by Duke Power. Now, don't ask me why Duke Power up from North Carolina decided to come down to Jackson, Mississippi area and build a natural gas or a combined cycle heat power plant. They did. And then a few years later, 5 or 10 years later, Entergy bought it from them. Now, I think that power plant, it's the nice thing about these like small modular power plant like this one is, relatively small. You can bring it online and offline pretty quick. So if you need more energy for, you know, a hot period in the summer, crank that little gas combined cycle gas turbine plant up and let her run. And when you don't need it, you can shut it down pretty easy. So that's the story of them, and that's why this is where I wanted to get to in this course, for you to be able to analyze a simple, relatively simple combined system. If you can do that, and it'll be on the final exam, but I'm going to coach you where you're going to be able to do them, then you're going to be in great shape. I think that's the last. Now we got another. Let's see. I think you read through that. I think I pretty much told you everything that's in that. This is called a heat recovery steam generator. You might also see it just called a heat exchanger, but it takes this air here at probably about, we need to work a problem to see somewhere maybe 700-800 degrees of hot air with no pressure energy, but a lot of thermal energy. And why not use it in this to generate steam for your Rankine cycle? Now, the one disadvantage is by the physics of it and the amount of airflow, amount of heat you have available here from your turbine cycle, you end up getting about 25%, well, about half the power out of your steam turbine as you get out of your gas turbine. That's just from the physics of how much heat's available here and how much heat is needed by the turbine. So let's say the steam turbine puts out 100 megawatts. You need about 50 megawatts to drive the compressor, so you have 50 megawatts left to go to your generator. If you're outputting 50 megawatts here, the physics end up, you'll be outputting about 25 or so megawatts here. So that gives you 75 total megawatts. But one way to look at it on this circuit down here, the Rankine cycle, this heat's free. It comes from this cycle, and it's not going to be used in this cycle. It's going to be discharged to the atmosphere unless you use it. So that's what makes these such great circuits. And let's see, I think that's about it. But the key to analyzing them is this right here. The way you have to analyze a system like this, you're generally given how much power you want out of this gas turbine. From that and the turbine and the compressor information, you can calculate what kind of mass flow you need flowing through this system to give you this power, net power out. That determines, of course, how much airflow you got through the heat exchange. From that, you can calculate how much you write your equations here. Your only unknown is the mass flow down here in your Rankine cycle. So, in one way to look at it, the amount of power you want out here determines, and combined with whatever compression ratio you're operating with, determines how much mass flow you need through this system. And we'll go through this and it make more sense to generate the net 50 megawatts you want. So that mass flow is determined by how much you want out of here. Now you've got this free heat. You can assume it's do analysis of this, and you can determine, you know what the state H here is and H here is of a Rankine cycle. So you can determine what mass flow rate of water this system can support. So once you know the mass, and you determine it by analyzing this thing, once you know the mass flow rate of water, you can heat up with this system up here. Then you can determine everything else and how much net power you get out of the turbine. And as I've said, if you get 100, say 20 megawatts of shaft power to drive a generator out of this steam turbine, you have this pump, but it only take, if you got 20 megawatts coming out, it'd probably take a half a megawatt or less, probably 250 kilowatts or so to drive the pump, almost negligible compared to what you get. So that, I think I'm going to end this video here, chapter 9, and I'm going to make another video working some problems, some gas turbine, Rankine cycle, Brayton cycle, and then a combined cycle. I think putting it all here at one time would be too much. I'll try to make that video tomorrow. And I'm not going to release, I'm going to release all these videos at one time, sort of like Netflix does. So you can binge watch. I don't imagine you will. It'd be body bored. But my goal is to get them ready to go by class time tomorrow or slightly later. Then you'll have pretty much 2 weeks to go through all of these videos, to work this next homework assignment. And then you'll be really ready for the final. And the final will be, I think, pretty straightforward and easy. It'll take you the full 3 or 4 hours, but I think you'll make a good grade on it. If you'll just look at these last videos, work this last part of homework, you'll be in good shape. Okay, that's it. See you later.